So as just to remind you, we're gonna have our exam March 15th, okay? And then today I sent out another homework 2. That homework is due next Wednesday, okay, before class. So next week on Wednesday, I'm gonna review homeworks, and also if you have any question, maybe I will answer your questions. And then the exam is, as I mentioned, is I'm gonna also send you a Zoom link. So I want everyone log into the Zoom. So during the exam, actually, I want to see you guys. Okay. What else? Okay, so I think that's all. Okay, let's begin our class today. So now, in the previous class, we studied about PN junction diode, right? So in the as a next device, we're gonna look at the so-called bipolar junction transistor. Okay. Oh, just 1 second. New? You didn't get my email? I think I sent the email again. Is using your City College mail. Did you get my email?
Let me check one more time, please.
Okay, okay. But anyway, maybe that one, maybe we can figure out after class, okay? If you didn't get the email. Okay, anyway. So bipolar junction transistor is basically, as this figure shows. In the previous class we study about, for example, PN diode, okay? So in the PN diode, we add one more junction, okay? So for example, if we put the PNP, then that's the BJT, okay? Or if you have NPN, that's also BJT, okay? So create the two junction like this, form this bipolar junction transistor, okay? So as you can see in here, because now you have the three material, for example, P and P. So each material we connect the electrode, okay, and then we name each this contact as the emitter, base, and collector. Okay, and then again, because we have two junction in here, so each junction we can apply either forward bias or reverse bias. So for example, emitter and base, this is the PN in here, is a PN diode. And base and collector, this is again, is an MP diode in here. So emitter and base, you can apply the bias. And then that bias can be a forward bias or reverse bias. Same way, collector and base, you can apply the bias. And that can be also forward bias and reverse bias. When you say forward bias, same way as we define in the PN junction diode, forward bias means in the P side, we apply the positive bias compared to the N side, okay? That's the forward bias. Reverse bias means that in the N side, now is you apply the positive bias compared to this P side. Okay, so that's just the basic is construction of this BJT. Okay, Okay, that's good. Now, I think you guys already learned this BJT from electronics class or some other class. So, as I mentioned, this is the three-terminal device. We have emitter, base, collector in this device. So three-terminal we define. And then this device terminal that form that PN junction. Okay, so you have a junction between the emitter and base, and then base and collector. Yeah. And then again, emitter and base, you can apply the forward bias, reverse bias, collector and base, the same way, forward bias and reverse bias. And then this is the symbol probably used in the electronics class to describe this bipolar junction transistor. And then the direction of this arrow represent the P to N direction. Okay, so that's the kind of is a symbol and then the description for this device. Okay. So first, before we go detail for this BJT, let's first briefly discuss about the fabrication of this device. Okay. So throughout the class, we're going to use the symbol to describe this BJT with like this PNP, this configuration, and then we put the emitter, base, and collector. Okay, so using this simple descriptive drawing, we're going to look at the operation of this BJT throughout the class. Now, if we look at the actual device on wafer, this following slide is showing that the typical device structures. Okay. So, for example, this is a cross-sectional view of the wafer. It's a device wafer. So, as you know, is that semiconductor device, especially this silicon-based electronic device, they all fabricate from planar structure. Okay, so on top of wafer is step by step. We're gonna create each layer of the device structures, and then so we form the device. Okay. And then the figure here is showing is that we actually cleaved this wafer, and then showing the cross-sectional view of this wafer. Okay. So the bipolar junction BJT structure is that at the first, this figure B, this one shows that the emitter is connected to the P side. Okay. And then base is they connected to the N side. Okay. And then the collector is connected to the P side. Okay. So that way is that we create a PNP transistor. Okay. And then to form this one is, as you can see, we have the series of these layers to form the PNP structure. And then at the end is we put the electrode to each this emitter base and collector side. Okay. So for this configuration is the B configuration. As you can see, is base and emitter is that located on the front side of the wafer, and then collector is located on the back side of the wafer, as you can see. Okay. So that is the one configuration. And then C shows another configuration. In this case, obvious difference for this structure is all the contact, which means that the emitter, base, and collector, all contacts are on the front side of the wafer. Okay, so By fabricating the device and their contact are all on the front side, so especially this configuration is useful when we integrate the multiple these transistors together. Okay, so to form the certain system functionality, you may integrate the many transistors at the same time, and then they need to be interconnected to create a certain functional system. Okay, so for that purpose, ideally we want to have all these electrode, emitter, base, and collector. Those electrodes should be accessible from the front side, okay, so that you can connect the interconnects based on your design. Okay, so this C configuration is the typical configuration we can see in integrated circuit for this device. Okay, so that's the kind of difference between this P and C configuration. P configuration, this is more like when you deal with individual transistor, as the component is for electronic component. So, for example, in the electronics lab, you may use the PJT as a single element. Okay, so for that kind of device or that kind of package, you can have the 3 legs come out from a single this component. Okay, so that kind of device may typically is following this kind of this configuration. Okay, so that's some difference between these two configurations. Now, in this following slide, I'm going to just briefly show how we fabricate the BJT from silicon wafer. So before we go this one sequentially, at the end, if we follow this structure, we're going to create the BJT is somehow from this kind of configuration. It has the emitter, which is connected to the N side of this structure, base connected to the P, collector connected to the N. So this one forms the NP N transistor. Okay, and then the device is that initially is fabricated from the P-type, this silicon substrate. Okay, so on top of P-type silicon substrate, at some point is that we're going to create this kind of a device, isolated device area for this single PJT. And then from there, using the subsequent this doping process, we're going to create the MPN, this structure. And then we put the electrode as a emitter, base, and collector. Okay, so that's it's a final device. And to make this kind of device is actually, this shows some sequence of the process. Okay, so first is that when you have the silicon wafer, okay, especially for this device, we start with a P-type silicon wafer. Okay, so as you know, is that the silicon wafer you can purchase is N-type or P-type or intrinsic silicon wafer based on your need. So for this case is that we start with a P-type, this silicon wafer. Okay. On top of there is first is that we actually make some opening with SiO2. Okay, and then we remove this oxide. And then by using this diffusion process, we actually create this N plus region on the P-type silicon. Okay, how we create this N plus region is this one is we call the doping process. So typical doping process is that, for example, if you have a p-type, this silicon like that, and then as I mentioned, is using the silicon oxide typically, we create the masking area, and then the certain area of the silicon oxide where we want to dope, we open using the photolithography. Okay. Once we open this one, now is this vapor is going into the furnace. So the furnace, typically the temperature of the furnace is that close to the 1000 Celsius. Okay. And then in this furnace, now we introduce the gas molecule, which form the N-type, this dopant. So we put the N-type dopant into this furnace, and then depends on the time. Now is this open, the silicon region, is they started to have this N dopant is diffuse inside the material. So it depends on the time and the temperature, and then other is a processing condition. We can actually control this diffusion process precisely. Okay, so once this ND doping is more than your P side, the dopant, okay, then now is that that area of the silicon is changed to the N plus region. Okay, so that way is that we change the a material to the N plus doping region. Okay, so that way is that we create N plus region. Then on top of in here is now is we perform the so-called N-type epitaxial layer growth. This one is different from this doping process based on the diffusion, because as you can see, this N layer is doping concentration is actually lower than this N plus region. Okay. When you use the typical doping process, all the doping process is actually convert the material to the higher doping level. Okay. In this case, is that actually is, if you look at in here, is that we start with the higher doping, and then is on top of there we create the lower dope to this semiconductor. Okay. This process is we call the epitaxial growth of semiconductor, which means that in this case, the silicon is the layer is actually is a growth from this surface of the silicon. Okay, that is called the epitaxial growth of the silicon. So using this process is that we grow the silicon, and then during the growth of the silicon, we can actually add dopant, and also even we can create a different doping concentration, which does not affected by your substrate. Okay, so using that process is we can now is grow this lower dope to this N-type silicon layer. Okay, once we grow that one, is now is again is we put the masking layer, and then using the SiO2, silicon dioxide, and then we open the certain area in the wafer, and then using this doping process, as I mentioned, we turn this N to this P region. Okay, so this one is a doping process. So which means that the dopant in the here is larger than this N side is the dopant. Okay. So by that way is that you're going to create this kind of structure in here. Okay. The reason is that we create this structure is that after go through the process, we're going to see that each individual, this kind of island, works as a single this BJT device. Okay, so you have the one BJT, and then next to this BJT, you can create another BJT. Okay, now between this BJT, by putting this P layer, is that when we have the different bias for the BJT, this P layer is actually isolate the individual device from other neighboring devices. The reason is that because you have the P in here, so when you apply the certain bias in for example, in this device, and then that bias is eventually need to go to the N to the P. Okay. Now another device you have the next to in here, and then you apply a certain bias, then that need to go to the N P, this kind of configuration. So whatever bias you applied between these two BJT, always one of the junction between the NP or PN, that turns out to be reverse bias, which effectively is block the current flow through the device. Okay, so that way is that you can actually isolate the individual device from neighboring device by using these P layers in here. Okay. Now, once we create the area of this transistor, the device, then now from there is that we're going to create the transistor. So again, is the layer in here. We open the layer, and then using the doping process, we change this N silicon to the P-type silicon. Okay, and then again we open the layers. Then we create N and then N. Okay. So by that way is that now we're gonna create this NPN structure, and then we just put the emitter electrode, base electrode, and collector electrode there to form the NPN transistor. So this way is that we form this transistor. Of course, this one just to show only one transistor, this fabrication step. But in fact, this is done in the wafer level, and then many devices can be fabricated at the same time. So you can actually have this many devices next to this transistor. Okay. So as I briefly mentioned, is that individual device is that that can be separated with these P layers in here, and then this individual, this transistor region is that we can also call this transistor top area to form the individual transistor. Okay, so this one shows that configuration. Okay, now here is the one thing is that I didn't mention from the previous fabrication is why we need this N plus layer. Okay, in fact, due to this N plus layer, when you form this N layer on top of P, we use the so-called epitaxial layer growth, which actually create the additional cost for the fabrication. Okay, but the reason we actually use this N plus region in here is that when you form the transistor, okay, So for example, if later on you will see the detail of the current flow in this bipolar junction transistor. But for example, is that when you have current flow from the emitter to collector, okay, the current flow is that roughly now is showing through this dotted this arrow, okay. Now, if you look at in here, is that the current passing is at some point is goes through this lower doped to this N region, okay? Which means that because this is a low doped semiconductor, this has the large resistance through this structure, okay? So without this N plus layer, right below this transistor, because between the emitter and the collector, when the current flow like this, it induced a lot of resistance in the semiconductor, so that this one is affect the transistor performance. Okay, so in the device fabrication, to reduce the resistance, especially in the lower doped this area, okay, we put this N plus region. So this area has the lower resistance. So that facilitate this emitter to collector, this current flow, okay, by reducing this resistance. Okay, so that's the reason is that why we use this N plus layer below this transistor. Okay, Janie, do you have a question?
Yeah, so for the for part A, do the electrons just not have enough like kinetic energy to go through the P layer or the bottom P layer?
Oh, this area, bottom P? Oh,
Yeah.
because when we apply the bias, for example, in the practical case, is that let's say emitter and base, we apply the forward bias. Then this is a PN junction. So the electron from the emitter that can inject it to the P side. Okay, and then because in the bottom P layer there is no bias applied in here. Okay. The current passing is that always is through these top layers.
I see. Thank you.
Okay. Okay. Yeah. Any other question? Okay, that's good. Okay. And then other thing is also is I want to mention for this structure is if you look at the configuration in here is that as I mentioned, we start with N silicon in here to form the device. And then next step is that using the doping process, especially in the base area, this area is returned into the P, okay? So from the N is that the donor is doped there, N silicon. We turn into this one to the P, we need to add the acceptor ions to change N-type silicon to the P-type silicon. Okay, so to do that is that the doping concentration, this one should be larger than the ND. Okay, so if we just compare the doping level, is that the N silicon in here compared to the base P silicon, the P silicon doping level should be larger than the N silicon in here. Okay, this is simply we use the diffusion process for the doping. Okay, now when you look at the emitter side, okay, the emitter side doping is starting from this P. Okay, so which means that now P side is again turning to the end of the silicon. Okay. Now, to do that is that the doping in here, emitter side, the ND emitter side doping should be larger than this base side doping in the P. Okay. So that is again, simply to fabricate this transistor, we use the diffusion process. Okay. For the diffusion, this doping, always you can convert the semiconductor from lower doped to the higher doped semiconductor. You cannot do is in the opposite direction. Okay, so that you have to be you have to understand in here. Okay, so typically is if we follow this fabrication step, as you can see, the emitter side is doping is always larger than the base side, and then in the collector side. So you're going to have this kind of sequence for the doping. Okay, that's good. Okay, so that describes the general idea about how we fabricate transistor. Okay. Now let's go back to the operation of this transistor. Okay. So this one is showing that the general concept of the transistor operation. So in a very simple structure, in here is showing that we have the P and P, this transistor. Okay. And then as we studied in the previous class, we already know when we have the P-N junction, we can apply the bias in the P-N junction. So for example, emitter and base, okay? And then this bias, we can apply the forward bias or reverse bias, okay? And then also, as we know, is that when you apply the forward bias in the PN diode, okay, between the PN, you can reduce the barrier height, okay? So at the thermal equilibrium, the barrier height is determined by the VBI, right? Now, if you apply the forward bias, barrier height going to be decreased by your applied bias, okay? So when you decrease the barrier height by applying forward bias, you're going to start to create a lot of diffusion current. Okay, so from the P side, you have lots of holes, they go to the N side, and from the N side, you have lots of electrons diffused to the P side. Okay, and then that creates now is your current in the structure. Okay, so same concept is that we can apply to this BJT operation. Okay, so in the BJT, for example, let's say this is the specific case. Emitter and base, we apply the forward bias. So this means that emitter P side, we apply the positive bias, then this base area, base side. Okay, that's the forward bias. In the base and collector junction, let's say we apply the reverse bias. Again, as you know, reverse bias means that in the P side, you apply the negative bias than this N side. Okay. So based on this condition, is if we apply this one in this BJT, you have the emitter, base, and collector configuration like this. And then when you apply the forward bias between the emitter and base, okay, now you're going to start to see is that the large of this majority carrier is moved to this base region. Okay, and then again, same way is that in the base, now you will have the electron moves in this is the P side. But if you look at in here, is as I mentioned, in the typical this BJT, the doping level is that the emitter side is always doped higher than the base and then collector. Okay. So when we apply the forward bias, as you can see, is that the number of holes actually moving to the base is much larger than the number of electron moves from the base to this emitter side. Okay, so that kind of information is you can see from the rough idea in here. Okay, now once this, for example, is the hole move to the base region, between the base and collector is we have the reverse bias. Okay, so this reverse bias is actually facilitate the hole move from this emitter to base. They can sweep through this reverse bias between the base and collector, and then finally this one contribute your collector current. Okay, so that kind of information is that you can actually see later on is that how this current actually flow through this structure. Okay. So in the transistor is that typically we define the total current through this device is such a way emitter current equals base current plus your collector current. Okay, so using this relationship, we can define the emitter current, collector current, and the base current. Okay, and then each current they have the current coming from majority carrier and also current coming from minority carrier. Okay, so for example, let's say if you look at the collector current, okay, the collector current has the current from majority carrier current plus current from minority carrier current. Okay, so for example, if the collector is that the N-type silicon, then the majority carrier current means that this one is the electron current, and minority carrier current means that this is the hole current. Okay. Same way is that when you look at the emitter or base, they all have the majority carrier current and the minority carrier current. Okay. So that's also is that you need to understand further this current for this device. Okay, so now, as I mentioned, is that when you look at the transistor has the two junction. So for example, PNP transistor, you have one PN junction in here, and then you have another PN junction in here. Okay, so you have these two junction. Okay, so each junction is that now you can apply the bias. Okay, and then the bias means that each junction also can be applied either forward bias or reverse bias. Okay. So this configuration now depends on the bias which apply to each junction. We can actually define different operation configure operation regions in this transistor. Okay, so for example, if the emitter and base is a forward bias, okay, and then collector and base also forward bias. Okay, so both junctions are forward bias. In this case, is that we name that operation region as the saturation region. Okay. If we apply the both junction reverse bias, Okay, that one we name as the cutoff region. Okay. Now, emitter and base, we apply the forward bias, and collector and base, we apply the reverse bias. This one specifically we call the forward active region. Okay. And then the opposite of this forward active region is emitter and base is the reverse bias. Collector and base is now we apply the forward bias. Okay, that one is with just 1 second. Okay. That one is we call the inverted or inverse active region. Okay. So later on, when we describe the this BJT, okay. So at some point is that instead of we name each these bias, we can simply saying the forward active region or saturation region, cutoff region as the device operation. Okay, so by this name, you should understand transistor has the appropriate their bias condition. Okay, so for example, if we apply the transistor in the forward active region, then you have to understand is that transistor emitter base going to be forward bias, collector base going to be reverse bias. Okay, so that you should understand is that as the different region of operation for this BJT. Okay. Another thing is that as you know, this device has 3 electrodes. Okay, we name as the emitter, base, and the collector. Okay. For the typical application to use this transistor, we use the transistor, especially bipolar transistor. Typically, we use as this amplifier. Okay. So when you use this device as amplifier, now is we need to have the input, and then we have the output. Okay, for the device. Okay, so depends on the which side you're going to use as input, and then the output. You're going to have the 3 is configurations. So for example, is that let's say as the base works as a common between the input and output. If we put the emitter and base as the input, okay, and then the collector and base as the output, this configuration we call the common base configuration. Okay. If we choose the emitter as the common, okay, then again is that as you can see, base and the emitter that works as the input, and in this case, emitter and collector works as the output. Okay. If you choose the now is a collector as this common, then collector and base works as the input, and emitter collector works as the output. Okay, so depends on the which electrode you use as common for the input and output. This configuration, you can have these 3 different configuration as the application side. Okay. Okay, so that's the also general concept. Now, this one roughly, this slide roughly shows that the current component in this BJT. Okay, so in the very simple example in here is that you have P, N, P transistor. Okay. Emitter and base is again, this is the PN junction. So you have emitter and you have the base, and then you have a collector. Okay. Emitter and base, you have a PN junction. Okay. And then the base and collector, you have another PN junction. Okay. So now is, for example, emitter and base, if you apply the bias, okay, and then also is collector and base, you can apply the bias, right? So here is that I have one question to you, okay? This one shows energy band diagram for this particular BJT. Okay. So the black line is showing that at the thermal equilibrium, okay, the energy band diagram of this bipolar BJT transistor. Okay. So first question is, how do you know is that this black line is at the thermal equilibrium? So can you answer?
Professor, because the Fermi level is constant throughout the whole device?
Yes, that's the correct answer. So as you can see is that because the Fermi energy level is constant throughout this energy band diagram, so we can see that now is this black. The energy band diagram is at the thermal equilibrium, okay? So that is the correct answer. Now, the red, this curve is, we apply the bias, okay? So we apply the bias so that your energy band diagram is changing, okay? Because we apply the bias, okay? Now, let's say, as I mentioned, this side is emitter side, okay? And then this is the base side, okay? We have doping. So emitter side is that the Fermi energy level is close to the valence band, okay? So which means that this is the P type semiconductor, okay? And the base side is, as you can see, is that the Fermi energy level is closer to the conduction band. So this is going to be N type silicon, okay? Now, if you look at the collector side, Fermi energy level is again closer to this valence band. So we can see that this is the P-type silicon. Okay, so that information we can see from this energy band diagram. Now, let me ask another question in here. Okay. So if you look at the energy band diagram, which is described as the red line in here, okay. Obviously, this red line is changing from the black line of this energy band diagram. Okay, so if you just look at this red line between the emitter and base, okay, how can you tell me is that how you apply the bias between the emitter and base? So can you answer the question?
So what's the question? Which bias we applied? Or
Yes.
the forward bias?
Is so how do you know?
Because in EV the whole when they get okay, if you apply the forward bias, the whole get obtain energy and then they go lower side.
Okay. Okay. So that's the, yeah, is It's partially correct. So if you look at it here, is that now is EV for the red line is actually move is from this black in the lower this side, right? So which means that if we can see is that compared to this base region, okay, in the emitter side you apply the positive bias, okay. So you apply the positive bias so that this is the energy band in the emitter side is moving down, okay. So by that way you can distinguish is that this one showing the emitter side you apply the positive bias compared to the base side, okay. So that is you can see. Now similar question is if you look at the collector and base, okay. Can you tell me is that how you apply the bias in the collector and base? So can you answer me? So as you can see in here is that initially there is no bias, okay. EV was in here, okay. Now when you apply the bias, is change it to this EV is going up like this. So which means that for this case is that this side you apply the negative bias, right? So that the energy band is going up, okay? So which means that this side in here, in the PJT, this is a P side, okay? And this is N side. So P side, you apply the bias negative, and that means that this side, you apply the reverse bias. Okay? So that information you can also get from this energy band diagram. Okay. Now, if you look at in here, is that when you apply the, for example, emitter and base, this one is again, as I mentioned, you apply the forward bias. If you apply the forward bias, now is in the PN junction diode, as you can see, initially this difference, this one is the VBI between the emitter and the base. Okay. Now, if you apply the forward bias, the barrier height is decreased by you apply the bias. Okay. So when the barrier height is decreased, now you can see is that the hole and electron, previously they cannot pass through this junction, is because the lower barrier height, you're going to start to see they're going to diffuse into this area. Okay. And then since the emitter side is higher doped than this base side, as you can see, you have more holes as they move to this base side compared to the electron in the base move to this emitter side. Okay, so that information first is you can see from this energy band diagram. Okay. So if we just compare this movement, the hole in the emitter that moves to the base, that contributes the so-called emitter hole current. Okay. Now, electron in this base then move to this emitter side, that contributes the so-called electron, the current in the emitter side. Okay. And since the electron moves in this direction, so the current direction is in this direction. So if you look at the emitter current, the total emitter current you can see is that from the Hall current plus this electron current, you can have the total, this emitter current. Okay, so that contributor now is emitter current. Okay, and then again, as I mentioned, because emitter side you have a higher doped, so the number, the magnitude of this emitter Hall current is much larger than the electron current. Okay, in the emitter side. Okay. Now that's the first part happens. Now, once the hole is injected to the base, okay, since the base and the collector for this particular case is a reverse bias, okay, that is clearly, as you can see, is the due, this energy band diagram show that way, okay. In this case, the reverse bias, so when you apply the reverse bias, you can effectively reduce the diffusion current, okay. Now, only current in here is that from the drift current. Okay. The drift current between the this base and then the collector side is now coming from this way. So, as you can see, is in the depletion region. As we apply the reverse bias, you're gonna start to increase the electric field. Okay, so between the base and then this collector side. Okay, and then when the hole is migrate is close to this electric field region between the base and collector, now this hole is swept by the electric field, okay? Because hole is the positive charge, and here is that the electric field is that this way, okay? So positive this hole, once they going into the depletion region, due to this negative potential in the collector side, you're gonna start to see that the hole is swept to this collector side. When the hole is swept to the collector side, that hole contributes the so-called collector side Hall current. Okay, and then that contributes this Hall current in the collector side. Now, similarly, you have the minority carrier exists in the P side. Okay, so this electron, when this one see this high electric field region, that also can sweep to the base region, and then that contribute this electron collector current. Okay, but since this minority carrier concentration is much lower than the diffused hole current in here, the contribution of this collector electron current going to be very small. Okay, but combine this Hall current and the electron current, which actually show in here, this combined with these two current contribute now is your collector current. Okay, and then that form that our collector current. So that way is that we define that now this collector current in here. Okay, and then again is simply the base current. We can calculate from the emitter current minus this collector current contribute our total this base current. Okay. If we look at now is the detail of base current, is how we define the base current in here is, as you can see, is that when the electron moves from base to this emitter, that creates this emitter electron current. Okay, this emitter electron current is the same way in the base side is contribute the base current. So emitter electron current is that the one part of this base current. Okay. Another thing in the base current is that if you look at the collector and base, okay, the minority carrier in the collector, due to the electric field, they can sweep like this, and then that contribute to this base region. Okay, that one we define as the collector minority carrier current in here. Okay, same one is that we define as the another part of this base current. Okay. Okay. Now is the last one is when the hole in the emitter, when that one injected to this base region, okay, and then when they pass through this base, some of this hole recombine with the electron in the base. Okay. So when this one recombine, okay, the electron supply in the base and then create the recombination. Okay. So supply the electron that create another part of this base current, and then that one described by this component, IB2. Okay. So if we add them all, and then typically base, when we define in the transistor, the inward, this one, we define the emitter current. Outward, this one, we define collector current. And then out, this one, we define the base current. Okay. So if you look at the base current in here, is base current going to be IB1, that one is this one, in the same direction of this base current. Okay. And then the plus IB2, okay, that one again is same direction to this base current. And then the IB3, but the IB3 is the opposite direction of our defined this base current. So we have negative IB3. Okay. So we have these three different components contribute this total, the base current. Okay. And then that defined as the IB1, IB2, IB3. And then as I explained in here, their origin going to be different. Okay. It's in this BJT. Okay, that's good. So that defined that all the current through this BJT. Another thing is this one is typically is I think in the electronics class you guys already learned BJT. Okay, so when you deal with BJT for the electronics 1 class, I can see is that we use the so-called circuit parameters for the BJT. Okay, and then here shows several circuit parameters we typically seen in the electronics 1 class, especially for design the amplifier based on this BJT. Okay. And then simply I just follow their definition in this slide. Okay. So one is we call the base transport factor. This one defined as the alpha t. Okay. And then the definition of this parameter we define as this parameter in here. Okay. And then this one is, as you can see, this one is a total hole current out of your total total hole current in the emitter side. Okay. So as I briefly mentioned in the previous slide, is that if you have the, for example, P and P transistor, okay, and then especially to use the transistor in the amplifier, we typically use the transistor in the forward region, okay, so which means that emitter and base we apply the forward bias, and then the base and collector we apply the reverse bias. Okay, so for that configuration is that the hole in the emitter side represent this emitter hole current, okay, that inject to the base, and then some of them going to be recombined in the base, and then rest of them is going to the collector, and then contribute the collector hole current. Okay. Now we look at this magnitude of this value, and then define this base transport factor. Okay. Ideally, we want to have all the injected hole current from the emitter that reach to this collector side. Okay. But again, as I mentioned in the previous slide, some of them going to recombine within the base, so that you lose those hole, okay, in the base. Okay, so that contribute some loss in the current. Okay, so in the circuit definition in here is that we define that this base transport factor alpha t, and then we look at how much this contribution from the emitter eventually leads to the collector side, this hole current, and then we define this alpha t value. Okay. And then another one is we define as a so-called emitter injection efficiency. Okay. The definition of this one is the injection efficiency. This one defined as you have a total number of this the emitter current. Okay. And then, as I mentioned, emitter current, some part coming from your hole, majority carrier, and then some part from your electron, that's the minority carrier. Okay. Now, out of this hole, the current is we define how much portion will be contributed from your majority carrier current. Okay. That defined as the emitter injection efficiency. Okay. And then also is that you remember we also define the alpha and the beta. Okay. And then the alpha is we compare the collector current and then the emitter current that define the alpha. Beta, we compare the collector current and then the base current that define this beta value. Okay. Specifically, as we know, is that collector current and the emitter current, they have majority carrier current and minority carrier current this way. So from there is we can have some relationship between the alpha and the beta. Okay. So anyway, this is nothing new. This is just we borrow the definition of this circuit parameters, which are typically used in the designing of the amplifier and the BJT. So what later on we're gonna do is we're gonna actually look at when we design the transistor, is a BJT, okay, and then typically when you look at the BJT in this device level, we have the parameters of doping and then some material parameter, and also some structural parameters like diffusion, the base width, or different parameters, right? So later on is what our interest is. We correlate this material and then the structure parameter of the BJT to these circuit parameters, so that when we design our device, how those design affect these circuit parameters. Okay, So that's what we going to do later on. Okay. So I remember that you guys, when you deal with PJT in this electronics class, most likely is we didn't consider about material parameter or device design, structural parameters. We just take the certain value for this circuit parameter, and then starting from there is we apply that on as the, some optical amplifier design using this BJT. Okay. Now in this class is later on we try to see is that how this material and the structure parameter affect this performance of this circuit parameters. Okay, so that's what we're gonna do later on. Okay. Okay. We have 3 minutes left. Okay. Let me. Okay, 3 minutes left. So maybe I will come back. This one is in the next class. If you have any question, maybe we have 3 minutes, so I'm gonna answer your questions. Do you have any questions?
I know that you mentioned that you would go over the homeworks, but I forgot when you said
Yes.
you would.
So that's going to be next Wednesday. So next Wednesday, you will do another homework, okay? So after I get all your homeworks, I'm going to review the homeworks next Wednesday in the class.
Sounds good. Thank you.
Okay. Any other question? No question? Okay. So again, is as you know, is you should receive your second the homework today. That is due next Wednesday. So just to keep in mind, you have to submit that homework. And if you do not have any other question, then I think we're gonna stop our class today in here. Okay.
Thank you, Professor.
Okay. Thank you, guys. Okay. Be safe.
You
And
too. Bye.
yeah,
Thank you,
see you
Professor.
next Monday. Okay. Thank you.